Good afternoon, my fellow mathematicians. This is Chance here. I'm recording my proof for theorem 60. Theorem 60 states f is uniformly continuous if and only if f is continuous on AB. And f is uniformly continuous on AB. And that's supposed to be a closed interval. My bad. There we go. So, we have our definitions for continuity using epsilons and delta. F is continuous means for every epsilon greater than 0, there exists a delta greater than 0, that's supposed to be greater, my bad again, such that if t is an element of the domain of f and x, the absolute value of x minus t is less than delta, then f of x minus f of t in absolute value brackets is less than epsilon. F is uniformly continuous on AB means if u comma v are in elements of a comma b and u minus v is less than delta, then f of u minus f of b is less than epsilon. So here's our proof. Case 1. F is continuous on a comma b. So that means we have an x that's an element of a comma b. If t is an element of a comma b, and x minus t is less than delta, then f of x minus f of t is less than epsilon by definition. So our proof is we're going to pick delta equals delta and epsilon equals epsilon. Then if u comma v is, if u and v are elements of a comma b, and u minus v is less than delta, then f of u minus f of b is less than epsilon, which we picked epsilon to be epsilon and delta to be delta. So they're both less than the same delta and epsilon. Therefore, if f is continuous on a comma b, that implies f is uniformly continuous on a comma b. Case 2, f is uniformly continuous on a comma b. That means that we can use the definition for uniformly continuous, which I figured we'd skip. So here's the quick proof. We pick epsilon equals epsilon. If x and t are elements of a comma b, and x minus t is less than delta, then f of x minus f of t is less than epsilon, and those are supposed to be in absolute values. My bad. Here we go. Therefore, f is uniformly continuous if and only if f is continuous on a comma b.